So in the previous lecture, we introduced the Dirac delta function. And you might remember that at the end of that lecture, I hinted that this function is going to actually have a deeper significance in the study of differential equations. And so that's what I'd like to talk about today. And we're going to start by introducing the convolution of two functions. So let's suppose that we have two functions. We'll call them f of t and g of t. So f of t and g of t are functions. And let's suppose that these have Laplace transforms. So they're functions with the Laplace transform of f of t being denoted by capital F of s, and the Laplace transform of g of t being denoted by capital G of s. So our usual notation. And I'd just like to recall an important property that we've used many times so far is the linearity of the Laplace transform. So what is the Laplace transform of f plus g? Well, it's the Laplace transform of f plus the Laplace transform of g. So it's, in other words, it's capital F of s plus capital G of s. Okay. And you might be wondering, what about this? What if we had the Laplace transform of f times g? Is that equal to capital F of s times capital G of s? And the answer is no. So this is not, in general, equal to capital F of s times capital G of s. So this is not what linearity means. Linearity means you can take if it were a constant times f, then you could take that constant outside. Or if you have a sum, then that's the Laplace transform of each part of sum separately, and then added together. But the Laplace transform of a product does not, in general, equal the product of the Laplace transforms. Let's just do a quick example to see why that's true. Let's take f and g to both be the function t. Okay, so the Laplace transform of t times t. So there are two ways I could do that. Well, we have a formula for the Laplace transform of t squared. That's just this formula here. Of t squared, the Laplace transform is 2 factorial, which is 2, over s cubed. So it's 2 over s cubed. Okay. But we could alternatively do the Laplace transform of t times t, which is not equal to what I'm writing down now. Right? And we can see that this is 1 over s squared times 1 over s squared, right, which is not 2 over s cubed. So that's an example where these things are not equal. So you want to be careful about saying that you don't want to say the Laplace transform of a product is a product of the Laplace transforms. That's not true. Let me actually box this word not just to emphasize this is not a property that we can use. Okay. However, there's actually a variant of this that is true, that does turn out to be true. So I'll write a variant of this. Does turn out to be true. But in order to make this equal to that, we actually have to replace this product with a different kind of product. And that's what the convolution is. And so we're going to define the convolution of two functions. And a convolution, we use this symbol. So that's the symbol for convolution of f and g to be. Okay, well, it's not simply the product of f and g. So what is it? So we use this symbol, f convolved with g, okay, or the convolution product. And we define that to be an integral from 0 to t of So these are functions of t. I'll just emphasize that. The integral of f of t minus u times g of u du, where u is just some variable of integration. Okay, so when I do this integral, I will not have u in my final answer. That's just a variable of integration. And I plug in these values here, and then I'll get some function of t. Okay, so this is called the convolution integral. And so the most important property of convolution is that it gives us a variant of this statement that does turn out to be true. So it turns out that the Laplace transform of the convolution of two functions, f and g, is equal to the product, this is an actual product on this side, of their Laplace transforms. Okay? So this is, I'll box this because this is really the key property of convolution that we're going to use. Okay. So the Laplace transform turns convolution into products. So this is the key property of convolution. Okay, so I'm actually not going to prove this property. You can prove it by just going straight from the definition. So we just take the Laplace transform of this, and then we have to prove that that's the Laplace transform of f times the Laplace transform of g. It just turns out that this proof involves some concepts from multivariable calculus. So I'm actually not assuming that you're familiar with if you're following this course. So in the first lecture I said that you want to be familiar with single variable calculus, but not necessary to be familiar with multivariable calculus to follow this course. So we're going to take this as a black box, but you can find various proofs of this on the internet. Okay. What are some properties of convolution? Well, before we get into that, I'd actually just like to do an example of an application of this statement. So convolution can be used. There are many ways convolution can be used, but convolution can be used to find inverse Laplace transforms. Okay, and you might see how that could work. So what if we have something in the S domain that we can write as a product of two functions, each of which has a Laplace transform that we can figure it out? Well, then the inverse Laplace transform is just going to be the convolution. Okay, so the inverse Laplace transform of these is just going to be the convolution of f and g, where f is the inverse Laplace transform of capital F, and g is the Laplace transform of capital G. So rather than just saying that, let's do an example. So let's find the inverse Laplace transform of this function. 1 over s squared times s squared plus 4. Okay. And of course, we don't need to use convolution to find this inverse Laplace transform. This is one that we could have done anyway. You might think about how you would do this one. The idea would be to use partial fractions. Split this up into two fractions, one with a denominator of s squared and one with a denominator of s squared plus 4. But let's see how we can use this. So what is my capital F and what is my capital G? Well, let's write this out again. So I have 1 over s squared. I can take that as my capital F. And then I have 1 over s squared plus 4. That's almost the Laplace transform of a sine. It would be exactly the Laplace transform of a sine if I had a 2 up there. Okay. But I can't change the problem, so I need to put a 1/2 out here. So here's what I'm going to do. I'm going to view this one right here as my capital F of s, and this one here is my capital G of s. Okay, so I have a capital F of S times capital G of S. And then when I take the Laplace transform, the inverse Laplace transform, I'm sorry, I should get little f of t convolved with little g of t, right, by this formula. Okay, well, what is little f of t? If capital F of S is this, then little f of t is, what is the Laplace transform? Or what is the function that has 1 over s squared as its Laplace transform? Well, it's just the function t. And what is my g of t? Well, as we said, it was a sine of 2t. So in other words, the answer to my problem is 1/2 times this convolution. So I need to do t convolved with sine 2t. Okay. Okay. Well, what is this? Let's write out a definition of the convolution. So we'll get some practice actually using this integral. Okay, it's the integral from 0 to t of, okay, I have a t and I have a sine 2t. So my t will be this f and my sine 2t will be this g. We're actually going to see it doesn't matter what order you do it in. But let's say t is my function f. So what do I need to write here? If f of t minus u, every time I see a t, I need to replace it with t minus u. So I have t minus u times g of u, so sine of 2u du. And I need to evaluate this integral now. Okay, so how would we evaluate this integral? Well, we could break this up into two integrals. So the first one is t sine 2t, or sine 2u du. And then we have minus 1/2 times integral 0 to t of u sine 2u du. Okay, and in this integral, the variable of integration is u in both of them, right? So this t is just a constant. So we just integrate sine 2u and then evaluate it at the bounds. For this one here, we'll need to use integration by parts. So we have a product of u and sine 2u. So this one we'll use integration by parts. Maybe I'll leave this as a problem for you to try. So a problem, I'll tell you what the eventual answer is though, so you can check. You could also check by doing this the old way too, using partial fractions. But problem, evaluate this integral. Evaluate this expression. Good practice doing some integrals. And the answer should be the following. So you should get 1/4 t minus 1/8 sine 2t. Okay, so you can already imagine how this might be very useful. How we can actually get an integral formula for the inverse Laplace transform of a product. Okay, that's what this allows us to do. In fact, let's add this to our chart. So the Laplace transform of f convolved with g is what? It is capital F of S, and this is a function of t, is capital F of S times capital G of S. Okay, which is multiplication. And so again, we can do this backwards. If we have a product of two functions in the S domain, then the inverse Laplace transform will be the convolution of their individual inverse Laplace transforms. Okay. So as I said before, I'd like to talk about a few properties of convolution before moving forward. So what are some properties? Convolution. Well, first of all, call this property 1. What is any function f convolved with the 0 function? Well, we can just stare at the definition and And we see right away that, you know, this whole integrand just becomes 0 if g were 0. And so we're integrating 0. Doesn't matter what the bounds are, we get 0. Okay. The second property is actually not so obvious. It says that it doesn't matter what order you use. You can do f convolved with g, and that's the same as g convolved with f. The reason I say it's not obvious is because this definition is not symmetric, right? We see f of t minus u and g of u, right? So this is not symmetric, or at least it doesn't appear to be symmetric. But this is true. Let's see why this is true. This is an example of using this definition. So what is f convolved with g by the definition? It's integral from 0 to t of f of t minus u times g of u. Okay. And yes, remember we're integrating with respect to u, not with respect to t. Okay. Well, I'd like to try to write this so that it's f of u and g of t minus u. And so I'll do that by changing variables. So let's do a change of variables here. Let's set v equal to this t minus u. Well, what's dv? It's just minus du. Okay, so what do we get? We get an integral from... wait a second, our bounds are going to change. These are the u values, right? So what are the corresponding v values? I use this formula. Okay, so my v value is t minus 0, which is t. And then my v value up here is t minus t, which is 0. So actually these flip. And now I have f of v times g of, well, what is u? U is t minus v, right? I'm just solving that one for you. So g of t minus v. And now du is negative dv, right? So I'll have dv, but I have to put a negative sign there. Okay. Okay, but there's a property of integrals that you can reverse the two bounds, but when you do that, you add a negative sign. So we already have a negative sign, so that will cancel out with that negative sign. And now I'll maybe rewrite this just so it's more obvious. I'll put the g part first and then the f part. dv. And what do we have here? Well, this is exactly our definition of convolution, right? But we see that f and g, the roles have now been reversed. I mean, of course, we have v here instead of u, but it doesn't matter what this variable integration is. We can call it anything we want. But yes, this is g convolved with f in that order. So it turns out they're the same. Okay, third property, I won't prove this, but it turns out that so property 2 is called a commutative property. Commutative. F and G are so convolution is commutative. Doesn't matter what order you do it in. And property 3 is called an associative property, so it doesn't matter how you group things. So if I have f convolved with g convolved with h, that's the same as if I did f convolved with g first and then convolved it with h afterwards. That's called the associative property. Okay, so what about this? So what is f convolved with 1? Well, we would think if this is acting like a multiplication, then it should just be f. But it's not true. It's not true that f convolved with 1 equals f. Okay. Again, I'll emphasize this is not in general true. Okay, let's do an example showing it's not true. What does t convolve with 1? By definition, it's if we go from 0 to t, and this is my function f, so I need to it's f of t minus u, so I need to replace all the t's with t minus u, so it's t minus u. There's my function g, is g of u. I need to replace the t with u, but I don't see any u's, right? It's just 1, so it's just times 1 du, like that. Okay. Well, what is this? You can evaluate this and you find that it's t squared over 2. It's not t. Okay. So 1 is not the multiplicative identity for convolution. However, there is a multiplicative identity. However, and let's call this our property 4. The multiplicative identity happens to be, yes, that's right, the Dirac delta function. Okay, so if you convolve with the Dirac delta function, you just get your function back, which is pretty cool. And why is this true? Again, so I'm just showing why these are true to get some practice working with this definition. I think it's useful. And so let's just write this down. So it's f of, well, f is a function of t, right? These are always functions of t. So it's f of t minus u times delta of u du, where this delta is the Dirac delta function that we introduced in the previous lecture. Okay. Well, as you might remember, this is only non-zero at u equals 0. Okay. And what does that mean? It means we can just replace, this function, we only care about its value when u equals 0. So we can replace it with f of t minus 0 in our integral. And this does not depend on u, so we can take it out. This is similar to the arguments we did in the previous lecture. And then what is this integral? We're integrating the Dirac delta function, but we see that the lower limit includes 0, which is where this has the infinitely high spike with area under the curve 1. And so this integral becomes 1. And so we just get f of t. Okay. Because, again, this is 1. And so we see that, this Dirac delta function sort of acts as an identity element. Multiplicative identity. Okay, so this is what convolution is and sort of how to work with it, but convolution has a much bigger significance. That's what I'd like to talk about. And this ties in several ideas that we've been talking about over the previous several lectures. So maybe I'll call this, so we're going to introduce the idea of impulse response, and the transfer function. You might have heard of this concept before, especially if you've taken some engineering courses, so transfer functions. Okay. So here's the setup. So suppose we have a system. It can be any kind of system we want, but we're going to assume that it can be modeled by, so suppose a system is modeled by a linear differential equation with constant coefficients. So linear differential equation with constant coefficients. As we've seen in this class, there are many systems that can be modeled by this kind of differential equation. Let's take one for example. So for example, a second order differential equation. We've seen a lot of those so far. Y double prime plus AY prime plus BY equals 0. So let's say there's no external force, and this is just representing some kind of system. It could be a mass spring system, it could be a circuit, it could be any other system that can be modeled by a linear differential equation with constant coefficients. Okay, let's suppose we don't know anything about A and B, so they're unknown. And our ultimate goal would be to predict how this system will respond. To an external force. Okay. So if we have an external force, how does that enter into this differential equation? Well, then we would replace this 0 with our external force, and then we have a new differential equation, an inhomogeneous differential equation that we can solve. But let's just suppose we have an arbitrary external force. Can we predict how the differential equation will behave subject to this external force? How our system will behave? And it seems like this is maybe something too much to ask, without knowing what A and B are. We can't solve the differential equation when we plug in a force here. But amazingly, the answer is yes, we can basically predict how this will respond. And we can do so with very little additional information. That additional information is sort of summed up by this transfer function. So let me talk about where this comes from. So first, what we do is we measure the response of our system to a unit impulse. So here's my force function. It's just this unit impulse. How do we model a unit impulse? That's our Dirac delta function, right? Delta of t. Okay. I.e., we want to solve the initial value problem. Y double prime plus AY prime, just our differential equation, plus BY equals, and now we are going to subject the system to a unit impulse. Okay. So in a circuit, for example, it could just be some pulse of energy, unit impulse. It's also important actually that we do this when the system is at rest. So we want both the derivative and both the value at 0 and the derivative at 0 to be 0. Okay, whatever y is, whether it's the charge in a circuit or whether it's the position of a mass spring. Okay, and let's actually let's establish some notation. So we'll denote the solution by, instead of y of t, I'm going to use the notation h of t, just because that's what's commonly used here. So this is the solution to this initial value problem. This is the response to a unit impulse. Or a so-called impulse response. And then I'm going to introduce one other term, the Laplace transform of h of t is going to be called the transfer function. And we're going to see very soon why it's called the transfer function. The transfer function. Okay, let's begin solving our initial value problem. So maybe I'll replace the y's with h. So h double prime plus a, h prime plus bh is delta of t. Okay, let's take the Laplace transform, and we get s squared of capital H of s, right? The Laplace transform of little h of s. And then remember the formula for the Laplace transform of a derivative. I now need to do minus s times h of 0, which is just 0, minus h prime of 0, which is also 0. So that's all I have. And then I have a times s times the Laplace transform of y again. And again, I don't have another term there because, again, our initial conditions are both 0. Plus b times Laplace transform of little h, which is capital H. And do you remember from the previous lecture what the Laplace transform of delta of t is? That's just the unit impulse at t equals 0. That had a Laplace transform of just 1. It was the simplest possible Laplace transform, maybe other than 0. Okay, what do we get when we solve for h of s, capital H of s? Well, we can factor out the capital H of s and then divide by this polynomial. This is actually the characteristic polynomial. We get 1 over s squared plus as plus b. Okay, so I'm going to box that. This is our transfer function. Okay. And, maybe at this point we're not sure how to continue proceeding if we want to find little h of t because we don't know what a and b are. But this is our transfer function. Okay, we'll leave it at that for now, and let's go to the next step. So remember, what do we want to do? We want to figure out not just how the system will respond to a unit impulse, but how it will respond to any external force that I put there. Okay, and perhaps we can measure, h of t here. Or if we can't, we at least have the transfer function. Okay, so next, let's suppose that we add an external force. Suppose an arbitrary external force. Arbitrary external force. And we'll call this f of t. Is applied to the system. Let's again fix some notation. So we'll denote the solution by y of t. So this will be the response to this f of t. Okay, just as h of t was the response to the unit impulse, this will be the response to this force f of t. Okay, and its Laplace transform we'll call a capital Y of s. Okay, well, what is the differential equation we're solving? I should have written that earlier. Well, it's our same differential equation. But instead of a 0 or a delta here, we put our arbitrary external force. And again, let's suppose at the beginning of this process, our system is completely at rest. Okay, that's an important assumption. All right, let's begin to solve this differential equation. Again, we'll use Laplace transforms. So just as before, we get s squared times that's capital Y of s. Plus, again, we have both initial conditions being 0, plus as times capital Y of s, plus b times capital Y of s, and that's going to equal the Laplace transform of little f of t, which we can denote as capital F of s. Okay. So I took the Laplace transform there. Let's again solve for y of s. Okay, so that's the Laplace transform of the solution y of t. Well, what do we get? We get this capital F of s times, you factor out the y of s here, and then divide by, again, the characteristic polynomial, so we get this. Okay. But what is this? Do we recognize this from before? That's our transfer function. So again, I'm going to box this transfer function when it appears. And so that's our transfer function. And this is actually saying something really remarkable, but before I comment on that, let's continue solving this. So what if we want y of t well, let me just emphasize what we have here. So capital Y of s is capital F of s times, we're in the s domain, times the transfer function, which we're denoting h of s, capital H of s. Now, if I take the inverse Laplace transform, what do I get? Well, I get little y of t. This is our solution to the differential equation. And this is going to equal the inverse Laplace transform of a product. Where have we seen that before? Well, you saw that earlier today, right? The inverse Laplace transform of a product is the convolution of the inverse Laplace transform of f, of big F, which is little f of t. And we're going to convolve it with Laplace transform of little h. Right? So what are these things? This is the impulse response. That's the response of my system to a unit impulse. Okay. So, the solution to this initial value problem is the impulse response. What is f of t here? That's the external force, right? And then what is y of t? That's just the response of my system to that external force. So it's the response of the system to the external force f of t. Okay, and this might not seem like much, right? We haven't really done much here. But I claim that we've actually uncovered something here really remarkable. What this is saying is, if we want a response of our system to any arbitrary external force, we don't have to know anything about the system, right? We don't have to know what A and B are. We just have to know what is our external force, and we have to know what is the response to a unit impulse. So, for example, if we've measured the response to a unit impulse, and we have any arbitrary external force, we can get our solution to the differential equation just by doing this convolution here. Okay, that's a pretty amazing, amazing thing. Also, if we know the transfer function, right? So, for example, let's say we have a circuit, and we know it's a complicated circuit, but we know its transfer function. Well, then all we need is the external force. If we know the Laplace transform of that external force, we can just multiply the transfer function by that Laplace transform of the external force, and we get capital Y of s, the Laplace transform of our solution. And then by just taking the inverse Laplace transform, we can figure out how our system will respond to this external force. Okay, so this transfer function is really important. It's intrinsic to the system. But by using Laplace transforms in convolution, we can actually just right away calculate how our system will respond to any external force. I just think this is a really cool idea. I want to kind of sum this up in a little diagram. So let's say we have our system here. I really want to think of our system as some sort of black box. We might not even know the inner workings of the system. It could be some complicated circuit. But we can input things and we can output things. So we input, for example, this will be our input. We can input this delta of t. And what do we get? We get some impulse response, some response to the unit impulse. Okay. Now, if we were to output instead any function, f of t, any arbitrary force. Okay. And let's recall this is some system. We don't really know the inner workings, but we know that it's modeled by a linear differential equation with constant coefficients. And now the question is, what do we get here? Well, here's what we get. We get f of t convolved with this h of t. Okay. All right. And basically, these observations that we've just made are the foundation of what's known as control theory in engineering. Okay, so we've basically come to the end of this course in differential equations. Maybe before we end, I'd like to leave you just kind of a fun little problem, or some kind of puzzle that involves Laplace transforms or convolutions. So I'd like to see you to see if you can find a function. I'll work through the answer to this problem too. I won't leave you hanging. But I want you to find a function f of t such that sort of this interesting property is true. If we take f of t and we convolve it with the function 1, we actually just end up with f of t plus 1. Okay. Of course, this is not always true for convolution. It doesn't just it's not just the same as adding the two functions. But see if you can find a function f of t such that these are the same thing. And feel free to pause the video, try to work through it yourself, and then I'll work through it in a bit. Okay, so hopefully you tried to work through this yourself, and there's a really nice trick here. First of all, you could try to use the definition of convolution, okay, which is this integral here, and you might have done that. And you end up with an integral equation, and then if you actually take the derivative of both sides and use the fundamental theorem of calculus, you get a differential equation, which you can solve for f. I'm not going to do it that way. I'm going to instead take Laplace transforms. And this is a typical idea, but it's surprising at first. So let's take the Laplace transforms. Of both sides, and what do we get? We get, well, let me just write it out. We get this. So we're now in the S domain, and so the Laplace transform of the convolution is what? It's the product, right? Of Laplace transform of f is capital F of s. The Laplace transform of 1 is 1 over s. And the convolution becomes a product, right? So that was our key property of the convolution. What do we get on this side? Well, we can use linearity here, right? It's just L of f plus L of 1. So we just get capital F of s plus 1 over s. And you now see the beauty of Laplace transforms. We just have an algebra problem. So we would like to solve now for capital F of s. So I can subtract this one. So I have f of s times, well, 1 over s minus 1. And that's going to equal this. Let's find a common denominator here because we're going to have to invert it. Okay. And finally, capital F of s is, well, the s's will cancel, and I'll just get 1 over 1 minus s. I'll rewrite that as 1 over s minus 1 and factor out the negative. Okay. Okay, we're not quite done. We need the function f of t. We found the function capital F of s. What is little f of t? It's the inverse Laplace transform of this, which is minus e to the t. So that's just a cute little problem, I think, that combines some of the concepts we've seen in these last few lectures. And so that concludes this course in differential equations. Thanks for watching. Hope you enjoyed.